Welcome back, everybody. This is Earth and Space Science 102. I'm Stephanie Welch, and today we're going to finish up talking about the solar system. So we've spent a little bit of time talking about the sun, by far the most important object in our solar system, and we'll continue talking about it a little bit more in the next unit because we're going to use it as a comparison for other stars beyond our solar system. We've talked in depth about all of the planets and objects in orbit around those planets, namely the moons. And now we have to talk about the thousands and thousands and thousands of other objects within our solar system, the ones that everybody seems to sort of forget because they're teeny tiny and they're seemingly insignificant. So today we're going to go beyond talking about 8 planets to talking about asteroids, comets, these things called Kuiper belt objects or trans-Neptunian objects, kind of a halfway point between Jovian planets and comets. And then we're going to also talk about meteors and meteorite impacts on Earth. So it should be a pretty cool lecture. We're going to be talking mainly about the very small and miscellaneous objects in our solar system. Now, as a reminder, for a couple of lectures back when we were overviewing the solar system, there's a couple of main places where you expect these kind of miscellaneous tiny objects to exist. One of them in the very, very inner solar system between two groups of planets, and most of them being out in the very, very excerpts of the solar system. So the asteroid belt, where of course you find asteroids, is located between the orbit of Mars and Jupiter. They're sort of leftovers in the terrestrial planet accretionary process, and those are going to be the first objects that we talk about. Then we're going to continue on to talk about comets. And comets, at least sort of in their native land and their natural habitat, they exist beyond the orbit of Neptune in the Kuiper belt and in the Oort cloud, which envelops the entire solar system sort of like a bubble of orbiting objects. That's also the kind of area where you find these Kuiper belt objects is in the outreaches of the solar system, the kind of no man's land, the cold, distant solar system. And then finally, we'll talk about meteors and meteorite impacts, and those are basically just names that we give for objects impacting Earth. And these little pieces of material can come from asteroids or comets. So let's start with asteroids. An asteroid is to a terrestrial planet as a comet is to a Jovian planet. The asteroids are basically just bits of rock and metal that were somewhat kind of stunted in their accretionary process. Unlike the terrestrial planets, you didn't have this massive snowballing effect that allowed for all of these individual pieces to coalesce together and accrete together to form one big object. Instead, they remained as sort of unattached individual little objects. So if you think about Mercury, Venus, Earth, Mars, you can see that the complete sort of innermost solar system where all these terrestrial planets exist is a place where you have very, very few orbiting smaller bodies and smaller objects. And this is because all of these much bigger, more massive objects have over billions of years of orbiting the sun have cleared their own orbit of debris. The bigger those objects are, the more mass they have. The more mass they have, the more gravity they have, and the more they attract these other little smaller objects. Now, out beyond the orbit of Mars and before you get to where you have Jupiter, so between about 2 astronomical units from the sun and 5 astronomical units from the sun, you've got this place where all of these objects haven't been capable of accreting together and forming a larger object. But even if they did, all the asteroids that are out there, their total mass would not be as large as even the smallest of the terrestrial planets. It wouldn't come anywhere close. In fact, if you took them all together and glued them all together to try to make a planet out of them, they wouldn't together come up with anything as big as the one asteroid that is the largest among all of them, the dwarf planet Ceres, which is technically an asteroid, sort of a big oblong, sort of smallish, potato-shaped object. So Ceres has a diameter of 1,000 kilometers, and in the image at the bottom of the slide, I show you one that has a, roughly speaking, sort of a total length, not really a diameter since it's not spherical, of only 56 kilometers. And that gives you a decent idea of the sort of range and size of these objects. Ceres being the largest, and some of the smaller ones maybe being even less than 50 kilometers long or so. They're all very oblong, very cratered, no real geological activity to speak of because there's no source of internal heat for long periods of time, but they're rich in the same kind of rocks and metals that make up the interior of our planet. Now, the reason why the asteroids are thought to exist in this location, again, in between the orbit of Mars and the orbit of Jupiter, is because of the presence of Jupiter. And I can't stress enough how important Jupiter is, having probably formed really early on in the formation of the planets in the solar system, how important the presence of Jupiter is in determining where objects wound up today. It's possible that Jupiter did a little bit of migrating around in the early days of the solar system. That would certainly make sense given our views of some of the solar systems beyond our own. It seems to be what's going on in those sort of environments. And the current day location of Jupiter is keeping this orbital resonance up, this effect due to the massive gravity of Jupiter that keeps all of these asteroids sort of as individual objects and keeps them from accreting together to form a solid object. It's similar to the same gravitational process that keeps the ring systems really close to a Jovian planet in check and doesn't allow those objects to accrete together to form a moon. So all of these individual asteroids don't collide together. They maintain somewhat of a distance from each other, and now you just have thousands and thousands and thousands of little bits of material all orbiting around the inner solar system just past Mars. So those are the asteroids, and the last thing I wanted to show you was where the main asteroid belt exists in a little animated figure. So everything in green here are the thousands and thousands, possibly millions of individual asteroids. And you can see how as you get closer into the inner solar system, closer to the orbits of Mercury, Venus, Earth, and Mars, they become much, much more sparse. They're not eliminated altogether, but they're going to be much, much fewer simply because those planets have already allowed for most of the collisions that would have happened. Not all, as we'll look at later. Certainly modern day collisions on a planet like Earth are still possible, but over time they become less consistent, less often. The next group of objects that we're going to talk about are the comets. Comets are to the Jovian planet accretionary process as the asteroids are to the terrestrial planet accretionary process. So the only real difference between the composition of a comet and the composition of an asteroid is the fact that comets contain all of these different types of ices, all of these hydrogen compounds in a solid form. And so again, we like to think of ice as solid water, and that's the main type of ice that exists on Earth given our range of temperatures. But it's possible for other hydrogen compounds like methane, ammonia, and so on, those to exist as solids as well. So because the temperatures, even in the early days of the formation of the solar system in the outer solar system, allowed for the condensation and solidification of some of these hydrogen compounds, these became components that built comets as well as Jovian planets. And the difference being that as you get further and further and further away from the sun, these objects become more scarce and they become sort of more distant from each other. So the collisions between the particles happen less often, and the objects themselves don't get to be as big, we think at least, as the Jovian planets. The Jovian planets formed essentially in a part of the solar system where you had the greatest number of these pieces of ice and rock and metal to build a core planet out of, big enough to then attract enormous amounts of gas. Now, these comets are most notable not as icy snowballs in the outer solar system, these kind of just icy mud balls or icy objects, but as really bright objects in the night sky. So I wanted to take a minute and touch on that. In the ancient civilizations on Earth, comets were always massively, massively feared. And there's a pretty good reason for this. If you don't really know that this is coming and you're really sort of relying on the night sky for your interpretation of when the seasons are going to change and what's going on, and your whole mythology is wrapped around your view of the night sky, then some really bright object that seems to come out of nowhere is going to really scare you. It's going to be something completely different. It might be an indication that the heavens are really angry at you. So the comet's always got a really, really bad rap. But all a comet is a really sort of bright object that's apparent for some period of time in the night sky, and then it goes away again, at least from that perspective. What we know to be true now is that the core of that object is a relatively small bit of ice and rock and metal. Now, because these things are stable in the outer solar system, when they get into the inner solar system, because they have very, very irregular orbits, they're then unstable. And a really cool process happens. The ice that makes up some of the core of this object, the relatively small object, turns directly into a gas. It skips that stage entirely where the solid turns into a liquid. It goes straight to a gas. It's called sublimation. And this gas then envelops that icy object like an atmosphere, and then that atmosphere trails out behind the comet as it moves into the inner solar system. It creates a longer and longer and longer tail as it dips closer and closer and closer to the sun, because as the object gets closer to the sun, it's moving faster and faster. If you remember, that was Kepler's second law of planetary motion, but it would apply to comets as well. So something like Halley's Comet, for instance, has a periodic orbit of about 80 years. And as it dips into the inner solar system, it's moving really, really fast and creating this effect of having a really long tail. And it's very, very bright because all of that gas becomes ionized by the charged particles that are coming from the sun, the solar wind. So then it's highly visible for that short period of time where it crosses into the inner solar system. But it's highly visible because it's effectively getting destroyed. It's like taking a block of ice out of the freezer and putting it out on the countertop. It's going to melt over time. It's destroying part of itself in the process. So with every pass into the inner solar system, the few comets that do actually do this and dip into the inner solar system are slowly disintegrating and leaving parts of themselves behind, leaving some of that ice and rock and metal behind. The ones that get closest to Earth will actually leave debris behind that gets in our orbit, and it will create the effect of meteor showers a little bit later on as some of that debris rains down onto Earth. So there are two places where the comets sort of naturally exist in their native land, in their natural habitat. The Kuiper belt, which is defined as being beyond the orbit of Neptune, about 30 times further away from the sun than the Earth is, 30 AU, to about 50 AU. So objects that orbit around in the Kuiper belt exist in roughly the same plane as the inner planetary solar systems, maybe with a slight little inclination away from that plane of the inner solar system planets. And that's why it's called a belt. That's why it's the Kuiper belt, because it's enveloping the inner solar system in just sort of one line, in one plane. Then as you get beyond 50 astronomical units away from the sun and then out to the very, very outer reaches of anything that could still be gravitationally bound to our solar system and our sun, you go from 50 AU to 100,000 astronomical units, or 100,000 times further away from the sun than the Earth is. And that is where the most distant comets exist in our solar system. Now, all it takes is a pass-by of maybe some other solar system, some other really sort of massive object, another star, and some of the objects in the very, very outermost solar system kind of get messed up in terms of their gravity and their relationship. Some of them even have unbound orbits where they'll dip into the inner solar system, sling back out again, back out into the reaches of space, and then never make a circle back around again. So there's a whole lot of chaos going on in this outermost area where you find comets, and that's the Oort cloud. And most notably, you don't have objects orbiting around in a single plane anymore. Instead, they dip in and out of that plane at crazy angles, sometimes almost vertical angles. And that's why it's an Oort cloud as opposed to an Oort belt. You have almost these comets encircling the inner solar system like a bubble or a sphere. Now, when those comets pass into the inner solar system, they leave debris behind. And some asteroids do the same thing. Some bits of debris left behind in Earth's orbit is always going to be there in changeable amounts over time. In the very, very early days, the earliest points in Earth history, the Earth would have been constantly bombarded with meteorite after meteorite after meteorite. It would have been a terrible, terrible time to be on Earth because every single one of those impacts would have utterly decimated the planet and eradicated any kind of life that might have been trying to take hold at that time. Now, meteorites impacting the surface of the Earth are relatively rare events, and most of these objects are small enough to never even reach the ground surface. They break up in orbit. So the name we give to basically anything that enters into the Earth's orbit and breaks up in the sky and leaves behind a bright ionized trail is a meteor. If that object actually comes all the way down to the Earth's surface, then we call that object a meteorite. So the meteorite is the actual solid material left behind, like my necklace up here. This is a little chunk of an actual meteorite. That is the material that actually reached the ground surface. Usually they have an iron-rich composition. And the objects that don't make it down to the ground surface are completely vaporized in re-entry by the frictional force of the Earth's atmosphere. Those are meteors. So meteors and meteorites have their name taken from the same origin that we use for the word meteorology. So meteorology is referring to what's going on in the atmosphere and precipitation coming from above. Meteors are coming from above. Meteorites are coming from above. And so they all sort of carry with it a common origin. I wanted to show you a picture of what these things actually look like as they're coming into the Earth's orbit and they're breaking up in orbit. Most of what we see is, again, not the meteorite itself. That's basically impossible to see from the ground surface. But we see this vaporized trail, this effect of having all of that solid material heat up so much that it becomes vaporized, and that trail that gets left behind is the part that's highly visible from the Earth's surface. So that's the part that you call a meteor or a shooting star or a falling star. It's all essentially the same thing, and it has actually nothing to do with stars. But because they're so bright, like comets, we tend to relate to them more like the bright objects that are distant in the night sky, stars, than as something that's relatively close to the Earth. The object that's creating all of this chaos is, just like a comet, incredibly small in comparison. And only if that object is really, really large does it actually reach the ground surface and do damage. Sometimes even an object coming into the Earth's orbit that doesn't reach the ground surface can come in at a shallow enough angle or low enough trajectory and get close enough to the ground surface that even if it breaks up in orbit, it can create a shock wave, and that shock wave can do a dramatic amount of damage. So there are a couple of different types of meteorites. We've referred to one of them already when we talked about the source of Earth's water, and that was something called a carbonaceous chondrite, and that's pictured up here in the upper right. An ordinary chondrite is very similar to a carbonaceous chondrite, but of course it doesn't contain carbon. So the carbonaceous chondrites and the ordinary chondrites, they're not only the source of Earth's water, they very well could also be the source of life on Earth. This is a really, really cool idea. It's completely, utterly unprovable, but it's a really cool idea about where the kind of spark for life that led to the evolution of life and the complexity of life on Earth that we have now came from. It's called panspermia. The idea that maybe even just the initial building blocks, the amino acids, or that some very, very primitive form of life actually traveled to the Earth's surface on or in one of these chondrites. So the chondrites, the carbonaceous chondrites and the ordinary chondrites, are relatively rare. Most of the meteorites that you see that have impacted the Earth relatively recently are iron or stony iron rich meteorites, like the ones pictured on the bottom three. So a meteor shower is a really cool event, not because you're watching stars travel across the night sky really rapidly and leave a bright trail of light behind. That's not what a meteor shower is about. It's about having debris coming into the Earth's orbit and breaking up. And we have a meteor shower when Earth enters into a really debris-rich part of its orbit. So this happens periodically throughout the year at really predictable times and coming from very predictable directions. So we have a very, very cool way that we go about naming these events. They are named for the constellation that they appear to be coming from. There are 88 official constellations in the night sky, 12 of which are the constellations of the zodiac. So things like Taurus and Aquarius and so on. Those are some of the constellations of the zodiac. Other constellations include things like Draco the dragon. So we call the meteor shower that appears to be coming out of Draco the dragon's mouth the Draconid meteor shower. They appear to be coming from several stars in that system. But as we know, they don't really have anything to do with the stars. They just appear to be coming from that direction. So that allows us to name these meteor showers based on the direction that they're coming from and when that particular constellation will be visible in the night sky. So this chart here just gives you an idea of when, generally at least, to expect some of these individual meteor showers to happen. Take, for instance, the greatest light show that the entire year usually has to offer us. It happens very early on in August. And it's also a fairly decent time to be outside at night. You know, you don't really want to be outside in the middle of the night in the middle of February. I did that once a really long time ago. I almost lost a couple of toes. If you're outside in the middle of the night and when the Perseid meteor shower is going on in early August, you're less likely to do that. The Perseid meteor shower, of course, is looking like the meteor shower. The incoming objects are actually coming from Perseus, the constellation Perseus, and that's most visible between around August 11th or 12th. These exact dates are actually for last year, the calendar year 2016, but this at least gives you sort of a range of dates to work with every year, and the dates stay very, very similar. Because again, for us to be entering into that debris-rich part of our orbit, it's going to happen at the same time every year. Another particularly good one is in December, the Geminids. Those meteors are sort of looking like they're coming from the constellation Gemini, which is most visible during the winter months. And that's most visible. The peak nights for that event are December 13th and 14th. So again, this just kind of gives you an idea of where the names for these meteor showers are coming from and when they're visible and what that meteor shower is really all about. The last thing I want to point out is that this debris can be left behind from any number of regularly occurring comets that enter into the inner solar system. Every time they do this, they leave behind debris. Comet Halley is particularly susceptible to this, having a very routine orbit that takes it very, very close to Earth. This is one of the most sort of periodic comet events. But other asteroids, other comets effectively do the same thing. And some of them break up entirely. They're on only a one-way trip into the inner solar system, and they break up entirely. So all of that material is left behind to then rain down slowly onto Earth and create a meteor shower. Now, the meteor shower is a really nice event. It's a really fun, very beautiful event. But the meteorite impact is anything but. If you have a large enough object that it is able to actually come all the way through the Earth's atmosphere unscathed, then when it makes contact with the land surface, it's almost ultimately going to do some significant damage. So I have a little sort of time-lapse picture here at the bottom that shows you the result of this impact. You actually have a complete liquefaction of the surface with a large enough impact event, and a gigantic crater can form from even a relatively small impactor. So while most of the bigger impacts, the ones that actually created the Earth itself, have happened a really long time ago and aren't capable of influencing life in any way because life hadn't really started getting going yet 4.54 billion years ago, the few recent impacts that we have absolutely changed conditions for life on Earth, and in some cases have created these events that we call mass extinctions. Now, only 50,000 years ago, an area in eastern Arizona was impacted by a meteorite. This meteorite carries the name the Canyon Diablo meteorite, and it's pictured over on the right of the slide over here. And you can then see, or a piece of it anyway, and you can see the gigantic crater that it left behind. A gentleman in the 1950s actually came up with the idea that this was caused by an impact. This was an actual meteorite impact, and his name was Barringer. That's why it's still the Barringer crater. You might know it better as Meteor Crater, Arizona. So this is miles across, a massive, massive impact, and the meteorite turned out to be what we call a primitive type meteorite. Radiometric dating of that meteorite using the uranium-lead technique allowed us to first understand the age of the Earth and therefore the age of the solar system. Because we think that everything formed together, we can use these primitive meteorites, the ones that have remained unchanged through processes like volcanic activity, to give us a fairly accurate age, as accurate as we could possibly come up with. So this only 50,000-year-old crater allowed us to date the material that created the crater to begin with and come up with an age of the Earth of 4.54 billion years. And that gives us a rough estimate for the age of the solar system as well. Now, probably one of the most famous impact sites is, again, relatively close to us. It's in the Gulf of Mexico, directly north of the Yucatan Peninsula, just offshore of the Yucatan Peninsula. It's called the Chicxulub Impact Crater. And this was sort of the smoking gun for a hypothesis that had come about before this crater was even discovered. Back in the 80s, a father and son team of physicists, Walter and Louis Alvarez, proposed this theory for the extinction event that most notably killed off the dinosaurs, but many other terrestrial and marine species on Earth about 65 million years ago. They found an extremely large concentration of the element iridium in a layer of rock that's coincidental with the end of where you find dinosaur fossils, with the event itself, this mass extinction event. And because iridium is in its greatest concentration in meteorites, they thought a large meteorite impact could have allowed for that extremely large concentration of iridium. And so it was somewhat speculative. It wasn't widely accepted until the Chicxulub impact crater was found in 1992. And when the impact crater was finally dated, its age turned out to be 65 million years old. So it was the smoking gun for the Alvarez theory, the meteorite impact theory for the extinction of the dinosaurs. So this is another massive, massive crater, but not nearly as well defined as Meteor Crater, Arizona, for two reasons. It's extremely old in comparison. It's millions of years older than Meteor Crater, Arizona, and it's underwater. And it's on a coastline where constant deposition is taking place and obscuring this impact crater. So we're lucky we found it, honestly. It took a very, very long time to find this impact crater. It wasn't an immediately obvious feature on the Earth's surface. Now, as this impact would have happened, you would have had an asteroid the size of Mount Everest, the size of the largest mountain on Earth today, flying towards the Earth to impact the Earth's surface and completely and utterly decimate the surface, sending up millions and millions and millions of tons of ash and debris into the atmosphere. And that's the clincher. That's what actually creates the extinction event. Not the impact itself, but the effect on the Earth's surface and sending all that debris up into the atmosphere. That debris would have been reflective. It would have cooled temperatures on the surface of the Earth to the point where the warm-loving dinosaurs and a lot of the other species that were dependent on the very warm temperatures at the end of the Cretaceous, they couldn't survive that impact. They couldn't survive the climatic repercussions of that impact. The last thing I'll mention about this impact crater is that when that impact actually occurred, when it hit the Earth, some geologists think that it had an effect on the geology on the opposite side of the planet. You might be familiar with the medical term of a contre-coup brain injury. This is the idea that you could basically hit one side of your head and that could cause bleeding on the opposite side of your head because your brain shifts around and slams into the opposite side of your skull. So the same thing theoretically could have happened to Earth as a result of this meteorite impact, a contre-coup planetary reaction, where this shook up the material in the inside of the Earth and created a volcanic event on the opposite side of the planet in modern-day India. So the Deccan Traps volcanic activity is thought at least possibly to be the result of the meteorite impact. And that too had its own round of climatic implications. So either way, it led to a massive die-off of many, many species, including all of the species that we consider to be dinosaur species today, except for one of their descendants, the birds. So these are all impacts that have taken place in the past, 50,000 years ago and 65 million years ago, my apologies. I wanted to at least sort of reference one potential impact that we have on the horizon that could potentially affect us during our lifetimes. There is an asteroid that has the rather ominous name of Apophis. This is sort of the counter figure in Egyptian mythology to the god of life. This is almost sort of the god of death, Apophis. On Friday, April 13th, 2029, this asteroid is projected to come extremely close to impacting the Earth's surface. The original estimations suggested that it had even maybe possibly a 2.7% chance of actually hitting the Earth's surface, but those projections have gone down with better math and better trajectories and so on. So we don't think it's actually going to impact the planet, but it is going to come incredibly close. So for scale, I have a little layout of all of the events that have come close to impacting the Earth and come between the Earth and the Moon. So of all of these objects, this asteroid, Apophis, is the only one that's supposed to come anywhere close to Earth and actually dip below our orbiting communication satellites. So it really just buzz cuts the planet. It comes incredibly close to impacting the planet. After that event occurs, after it comes very, very close, given its exact trajectory, we'll know whether 7 years later it's actually going to come back around and impact us. So if you have any questions on whether or not it's necessary and important to fund NASA, it absolutely, absolutely is, because it's only going to be advanced scientific technologies that are going to allow us to combat something like this, or even greater into the future objects that are currently unknown that could eventually impact the planet. Bruce Willis will most certainly not be available to go out into orbit and blow this thing up. So we're going to have to come up with technology to be able to combat an event like this, unless we want to face the same sort of extinction event that killed off the dinosaurs. Okay, so moving beyond meteors, meteorite impacts, there's one other group of objects that contain probably one of the most popular objects in our solar system that I still want to talk about. This group of objects are called Kuiper belt objects, and they currently include what used to be the 9th planet of our solar system, the most beloved object, Pluto. Now, Pluto was discovered in 1936 by Clyde Tombaugh of New Mexico. And in New Mexico, they are not acknowledging that Pluto is no longer a planet. Pluto has not been a planet since 2006, but they're playing hardball. They are not allowing for the idea that Pluto is not a planet anymore. And they're certainly not alone. If you go out and poll a random audience, they do not accept that Pluto is not a planet anymore. Now, the reason why astronomers voted to vote down Pluto in 2006 is not because of any sort of malice towards this particular object, but because it makes absolutely no sense to call it a planet. You basically either have to consider potentially hundreds of other objects that are just like Pluto in the outer solar system. You have to call all of those objects planets too, or you have to demote down Pluto. But because this was the first to be discovered, mainly because it actually crosses the orbit of Neptune. It gets relatively close to Earth, close enough to actually have been spotted. People really are attached to this particular one, if possibly only for all the mnemonic devices that you had to learn in grade school that had a P at the end, like maybe pizza or something for Pluto. Now we only have the 8 planets, and it makes way more sense this way. A group of 4 terrestrial planets that all share common characteristics, a group of 4 Jovian planets that all share common characteristics, and then Pluto with its icy brethren out here in the outer solar system. Now, Pluto and all of its other icy brethren, a much larger object called Eris, a somewhat goofily named object called Makemake, and some other of these Kuiper belt objects, all share the common characteristics of being roughly spherical. So they're unlike comets in that respect. Comets tend to be a little bit more oblong. They don't have the self-gravity to become spherical. They're typically larger than comets, but smaller than planets, and so that's why they're referred to in some cases as dwarf planets or Kuiper belt objects. Another name that they get sometimes are trans-Neptunian objects, because these are beyond the orbit of Neptune. And so if anything immediately pops up by having all of these different names for an object like Pluto and some of the other objects that are like it, it's that we're still figuring things out with regard to these objects. We're still trying to categorize them and understand them. They all have very inclined orbits compared to the regular sort of planar path of the interplanetary solar system objects, the inner solar system planets. So while take, for instance, Neptune and Earth have a more circular, but not perfectly circular orbit, and they exist in the same plane, Pluto would appear to kind of dip in and out of that plane on a little bit of an angle, and Pluto would appear to have a much more elliptical orbit. So it gets a lot closer to the sun, actually having it cross the orbit of Neptune and taking it much further away. And that's the classic hallmark of any objects out there in the Kuiper belt. As you get further away from the sun, essentially the force due to gravity diminishes and the orbits become more chaotic in many different respects. So I wanted to show you, in comparison to Earth and Earth's moon, the kind of size and scale that we're talking about for some of these Kuiper belt objects, including, in some cases, the moons of some of these objects. So take, for instance, Pluto in the picture at around 2,000 kilometers across, and right next to it, in the second picture, its moon Charon. One of the things with Pluto that you don't get with some of the inner solar system planets is that Pluto and a lot of its other sort of icy brethren out there are all incapable because of their size and mass of really clearing their own orbit of debris. And in a lot of cases, they have very, very large companions. So take, for instance, Pluto has a moon that's half the size of that planet, whereas our moon is a quarter the size of the planet. And that's even fairly unusual for a planet. So you can even see that Pluto is not even the largest. So trying to call it a planet would necessitate calling absolutely this dwarf planet Eris, or this Kuiper belt object Eris, a planet as well, because it's far larger than Pluto. Now, in part because it was originally a planet, and in part because it is one of the easiest effectively to study, NASA commissioned a 10-year mission. It actually took 10 years for a probe to leave Earth and travel all the way out beyond the orbit of Neptune and take many, many, many pictures of Pluto. So I have a before and after picture at the bottom of the slide that gives you some understanding of what our knowledge and what our information about Pluto was like before, when we had just the images from the Voyager missions, to get some idea of the look of Pluto and its companion Charon. And then Pluto afterwards, Pluto with this more advanced understanding of what's going on. So we think that there is some very small amount of geological activity going on. This is really all new information that comes about from the New Horizons missions. While you do have a completely icy surface and surface temperatures of 40 degrees Kelvin, which would be the equivalent of negative 600 degrees Fahrenheit. You have some geyser activity. You have a little bit of sort of interesting activity going on the surface of this planet, effectively making it as interesting as maybe some of the Jovian planet moons, and roughly around the same size as maybe some of the Jovian planet moons. Now, in 2006, I can't stress this enough, they demoted Pluto. There was a total outcry about this, but the International Astronomical Union voted to break down Pluto from being a planet in its own respect, the 9th planet of our solar system, to a Kuiper belt object or dwarf planet. It's not alone. There are hundreds and hundreds of other objects out there just like it. But Pluto was always sort of the most popular and the one that for a short period of time had this understanding of being a planet. So Pluto certainly is not impacted by this in the slightest. Pluto doesn't care. Pluto's out there with its icy brethren out in the outer solar system, and I think we need to eventually come to accept this, because this did come down 11 years ago. It's been 11 years since Pluto is technically considered to be a planet. All right, so that's Pluto and some of the Kuiper belt objects, and we also covered in this lecture a myriad of other sort of teeny objects in the solar system: comets, asteroids, meteors, and meteorites. So in total, the one thing that you can kind of take away from that just sort of cements this into one big lecture is that all of these are relatively tiny objects. These are somewhat miscellaneous objects in our solar system. Now, as we look forward into the next unit, we'll see that all of these sort of objects, terrestrial planets, Jovian planets, asteroids, comets, Kuiper belt objects, and so on, are thought to exist in every solar system, or at least in most solar systems, that the idea of having planets and asteroids and comets is not unique to our own system. There are billions and billions of stars, and our sun is just one of those stars out there in the night sky. And so from here on out, from the end of this unit, the second unit, into the third unit, we're going to broaden our perspective and begin to look at some of the rest of those stars and conditions that might be present around some of those stars, and how we begin to kind of compare those. So of all 3 units that I teach in this class, coming up, this next one is absolutely my favorite, and I hope it'll be your favorite too. Until next time, keep looking up.